In this video, we're going to learn about the epsilon delta proof of a continuous function, which is a rational function at a given point. So prove that fx equals x over z plus I is continuous at z not equal I. So you can see that it's a point in z not equal I, and we have a rational function. So let's see how we're going to proceed with this. The starting point for a problem like this is we're going to select a epsilon, and we don't have control over that. We just get an epsilon, and then we look at this difference. So this is how we normally do a problem. We always look at the difference. What's the difference? One is the function fc, and the other one is fz naught, whatever the point fc naught. So fc minus fc naught. And then what we do after that, we're going to simplify this one. We simplify, we substitute and simplify. So we can substitute to the two functions and simplify, and you can see that you can do the algebra and you end up getting this one. Now what we want to do, this one is familiar because that's coming from the delta condition, but everything else you need to eliminate, especially the variable terms. So this term z plus I. But you can see that this term is in the denominator. Since this is in the denominator, what we try to do, we try to find the smallest value. If it is in the numerator, we try to find the largest value. If it is in the denominator, we try to find the smallest possible value. So we need the smallest value. Smallest value. So how to do that? What we're going to do, we're going to consider a special neighborhood around I. So let's do that. So we look at a neighborhood. So your goal is to find the smallest value of z plus I, epsilon of z plus I. To do that, we can look at the special neighborhood. I mean, we just pick one for simplicity. You can pick any value you like. And then you can see this is the neighborhood we get. So it's around I, and then one epsilon, one radius is 1. So now the question is, if you find a z on that open disk, what is the largest absolute value of c plus I? It's not c plus I. So we try to use like normally when you get a problem like that, we try to use the reverse triangle inequality, not the triangle inequality, because it's in the denominator. So you have to go reverse triangle inequality. But you can see if you try it in this time, it doesn't work because you get a 0 as the smallest value if you use that. So that doesn't really help you. So we try to use a different approach. Because actually if you want to use the reverse triangle, this is what we normally do. So we look at the quantity. So what is z plus I absolute value? If you use the reverse triangle inequality, this is what you get. You get the absolute value of z minus the absolute value of I. But you can see in this domain, since c can be equals to I, you get actually 0. So this doesn't help you because you need like a non-zero value here. So that means we are not going to use that for this problem. So instead what we do, we use like a really nice geometric approach for this one. We're going to parameterize any point inside this disk. So what we do, we're going to parameterize any point in the disk using this parameterization. We discussed this earlier when we in the parameterization video, we talk about how to parameterize a point in a circle. So I is the center. So this is like A plus R E I theta. That's a formula. So here A is the center, which is I in this case. So it's a I plus R E I theta. And R, you can see, it's not just the boundary. It should be anything inside. So that means R has to range from 0 to 1. 1 is not included because the boundary is not included. You can see all of these points are really important in the proof. You will see what happened. So R is ranging from 0 to 1. Now let's try to evaluate c plus I. So we're going to plug in. When you plug in, you get 2i plus re I theta because there's another I in there. And then you can see it is still difficult to make any arguments with this. What we do, we're going to split I theta using the Euler's identity. We know that the I theta is equals to cosine theta plus I sine theta, or normally called cis theta. So we use that, we substitute that here. And once you substitute and collect terms, and you can see First you substitute, that's what you get, and then you collect terms, this is what you get. Now we can actually make an argument here. So the idea is, let's see, now let's look at the absolute value. So if you look at the absolute value, what we normally do is square the real part plus square the imaginary part and add them and take the square root. So this term is fine because you can see that since cosine theta and r, both of them can take values between, actually r can take only values between 0 and 1. Cosine theta can get values between -1 and 0. So that means what will happen to the first term is, you see that's greater than or equal 0. It can even be equal 0. So that doesn't help you much. But let's look at the second term. You can see sine theta is in between -1 and 1. But r is between 0 and 1. 1 is not included. It never get the value 1. So because of that, you can see r sine theta is actually in between -1 and 1 without the corners. So it never get 1. This is really important. That means the maximum, you can actually subtract from 2 is -1. Because you can see that r sine theta, the smallest that it can go is -1. Smallest value is -1. So that means you always get at least 1. So that means this term is actually bigger than 1 always. So this term is bigger than 1 always. So because of that, you can see when you add them together, the sum is bigger than 1. When you take the square root, it's also bigger than 1. So that's exactly what we need. So that is the smallest it can get. Actually, it never reach that value because r is never going to go to 1. But you can see that is the smallest possible value. Smallest possible value. So now we can actually continue the argument. Let's look at the rest of the argument. So we can see now as absolute value of z minus c, absolute value of fz minus fi. We simplified this earlier, and then what we do, we're going to break into. So what we do instead of, and you can see this term is clear, and we break it into, and then also you can see we switch the order because it's absolute value. So you can switch the order because normally when you simplify this expression, actually you get I minus z, but you can flip it because of the absolute value sign. Now you can see instead of c plus I, we put the smallest possible value. When you put the smallest value, you get the largest. That's why we have this greater than sign here, less than sign there, because on the right side is bigger because you pick the smallest value here. So that is the argument you need to understand here. That's the smallest value. You pick the smallest value, so that means you get the greater. It's the greater than sign. Okay, and then what we can do is now you can see, so it simplifies well, and you end up getting 3 absolute value c minus I. 3 absolute value z minus I. Now you want to make sure that you find a delta that satisfies the two conditions. One is you want to make sure that it's less than 1 so that we have the bound works. And where this epsilon over 3 coming? So the argument is you try to make this product less than epsilon. That's what we're trying to do. That means if you solve for a z minus I, if you solve for c minus I absolute value, what do you get? Let's try to solve for z minus I. If you solve for z minus I, you can see that you get epsilon over 3. So that's where you get epsilon over 3 term. Because that is when you simplify, when you solve for the epsilon sign, you get this. Good. Now you can see, so what we're going to do, we want to make sure that both are satisfied. So what we do, we're going to pick the smallest of the two. What is the smallest of the two? One is 1, that's for the upper bound, or in this case lower bound, and then epsilon over 3 coming from there. So we pick the smallest of the two. So that means if you pick any value where the absolute value of z minus I less than delta, since this is smallest value, the satisfies any such z satisfies both of them automatically because that's the smallest one. So now you can write this one. So let's make the argument now. So according to this one. So we see the absolute value, the difference of the absolute value is less than 3 times z minus I. That's we already get that from the top. And then the next part, 3 is there, that's fine. And then but since we pick a delta such that c minus I less than delta, you can see both of these conditions are satisfied, the first and the second. So you can pick whatever you want. So I pick the second one now because we know that it's smaller than the delta. So that means that's a smaller delta, but your other values can be bigger. So you can see it's automatically inside that. That's the delta neighborhood. And the other one, we don't know whether 1 or epsilon over 3 is bigger because we know that delta is inside this. So that's the argument we're going to make. So it's automatically inside. That means both of them are satisfied. So we get the condition, and you can see it simplifies to epsilon. So that is the argument we make for a problem like that. And that's exactly what we improve. And then this says that the limit is 3 over I, which is the limit at c equal I. So therefore, by the definition, f is continuous at z equal I. So this is how you make like a problem like this one, and just try to like kind of fully understand all the arguments that we make here. So now what we can do, you can do few practice problems. So use the definition to practice these problems. So there are like a couple of different ones that you kind of need to like know at this level. So you can try these. So and then this problem is like very similar to what you had earlier. And then we also have two most common ones, z and the constant function, and we also have another rational function, only the algebra is different here. And we have also like interesting problem. So 1 over z on this interval, what we call the punctured disk. So we have everything except the origin. So we remove the origin and we have everything else on c, called punctured disk. And then we have a cubic function, and also we have the z over z bar. We know that this, we talked about this function earlier, but the reciprocal of this function. We know that this function actually continues everywhere except 0. So let's try to give an actual proof for this one. And then also the real part on the complex plane, real part and imaginary part, both are continuous on the complex plane. So this is like a some problems that you can try. Thank you.